Thanks so much, Nikolai. Is this on? Can everyone hear it okay? I think I hear myself. Okay, great. Thanks, Nikolai. It's really great to be here. Every so often, I feel like I do a lecture in 6858, and I really enjoy it. And I often get really good questions. And sometimes, there are things that we still argue about internally, and sometimes it's like things we haven't thought about, and we're like, oh my God, do we have a bug here? And so I have some slides, and we can kind of do all the slides, but it might be more interesting just to talk about what you want to know about. And I actually saw a bunch of those questions submitted were really good. So we'll just see where it goes. And I know in the reading notes, so I'll get into it a little bit later, but we published a white paper that's a lot of this material, and we said don't read the whole thing because it goes on and on and on and on. But some of the stuff that in the slides is like the parts of the white paper that you didn't have to read. So we can discuss those because it's interesting, but we'll see where it goes. Okay, so as Nikolai said, the backstory here is that I was a co-founder and CEO of Keybase. We kind of kicked that off around 2015, and things were a little bit different back then with encrypted messaging. I feel like I think probably a lot of people use WhatsApp or Signal, but I think back then, it was a little bit more of the Wild West, and so Keybase came along, and we had some ideas for, I think we were thinking a lot about encrypted Slack, and so we used Slack, and we wanted it to be end-to-end encrypted, and we kind of worked at it from that angle, and I think like maybe a Signal kind of was coming at it from the SMS angle, and like wanted to replace your SMS client with Signal. So anyway, we spent a fair amount of time building out Keybase. It was really a lot of fun. It was a very challenging project, and we had to figure a bunch of stuff out. I think we spent a lot of time thinking about multi-device support from the very beginning. And if anyone uses Signal, like the multi-device story isn't great. I think WhatsApp just recently, just within like the last 2 or 3 months, just changed their multi-device story, so it's a lot better. But this is the kind of thing we spent a lot of time thinking about. In May 2020, we were bought by Zoom, and ever since, the whole team kind of moved over, and we still maintain Keybase, and it's something I use, and I know Nikolai's research group sometimes uses it too, because for whatever reason I'm in that group, and I get to hear about what they're having for lunch, or what papers they're doing. But anyway, but we spend most of our time just taking all the lessons that we learned at Keybase and just applying them to Zoom. And obviously, it was fun to run our own company, which we did for 5 years, but we got to Zoom, and obviously the scale was way bigger. Obviously, hundreds of millions of people probably use Zoom every day, and so it was a chance to take all this cool technology we had and apply it and have a lot more impact. And so that's kind of what we've been doing. So I had overall idea here is I want to give some quick background on video conferencing and some very rough sketches of how it works, and then talk about more or less phase 1 in the paper, which is end-to-end encryption for Zoom meetings, and that's actually it's in the app and it's running, and I use it every day, but unfortunately it's very hard to find, and so I've heard that MIT's Zoom account makes it basically inaccessible, but if you have your own personal Zoom account, you can enable it. It's unfortunately it's buried in the settings, but it does work, and I use it all the time. Anyway, and then after phase 1, we have all these other ideas for how to improve identity, and so that's phase 2+. We can talk about that, and there's also room for Q&A. Okay, so how does video conferencing work? And here's a very basic idea of let's say a Google Meet, or a lot of them are on this kind of architecture. So you have Alice and Bob, they're chatting with each other. They probably are doing everything over TLS, just they have a WebSocket connection open. And basically this is point-to-point encryption where if Alice is at Starbucks, she's sending her data over the Wi-Fi, but the barista can't access the data because it's using TLS. But when it gets to the server can decrypt it and send it out to Bob. I think a lot of, and I don't know this for sure, but I'm pretty sure a lot of the conferencing software that's set up in this way, where everyone's basically talking TLS to a central server, I think they do this very important thing, which is re-encoding for someone on a mobile phone. So if you think like Alice and Bob, if they're like both on wired connections, they can obviously have pretty good quality, and they're probably sending out just like full frame video as like, as fast as their network can handle it. But if like, Carol shows up on a mobile phone here and she has like a really spotty connection, I'm pretty sure the server is just kind of downsampling and sending like a more compressed version to Alice, and make it so she can understand the conference better, even though she's on a bad connection. And I think what this implies is that the server really needs to know. It needs to be able to decrypt and actually access the data, and so it can encode it, re-encode it for Alice. And I don't know of any kind of video encoding system that you could perform this, over ciphertext, right? So it's basically something you need the plain text of the conversation in order to re-encode for somebody. And that's like, I think that's typically the way like, Google Meet and WebEx and Teams. I think that's the way they're all working. Okay, so what's wrong with this? So I think at the basic level, the problem is like if you imagine the server becomes the bad guy, right? And this is like in secure distributed systems, it's a lot of times the assumption people make. And it's not, is this a reasonable assumption that like the server is good or bad? Well, we can kind of think a little bit about it. Who's able to attack a system, right? Like let's say, a Teams or a Meet. Well, it's like anybody at the company can do it. If they have access to the production servers, they could probably like, plug something in, like listen to the traffic going across. And the bad guy here, all they have to do is really listen. And so if you're good at this, you can kind of like break into a server and just listen and write everything down, and it won't leave much of a trace. So, it seems like it might be possible just to pull off this kind of attack. And in like the cloud world, like you have a stack of different people who could be performing this. And so, if you're like, Google probably, they run their own hardware probably, but like, let's say you're, some other like smaller video conferencing provider, and like, you're running in like AWS, and now like the AWS administrators and the people running the software, they could also, access what's going on in the machine. And there's also this notion that if somebody, gains access to like the perimeter, and, this could obviously happen through like a million different ways to hack. A lot of times in these systems, there's like a security perimeter where once you get in, there's a lot of mutual trust across the system, across the machines. And so, once you get past the perimeter, you can now get access to the machines that are doing the relay of the video, and then you can listen in on a video conference. If you think about this, like especially during COVID, like a lot of important stuff is happening over these meetings, right? Like it could be, a Fortune 500 board, a big company's board meeting. It could be Ukrainian officials talking to U.S. senators, and this actually, there was a news story about that a couple of months ago, and I think like some U.S. senators leaked that this was happening, but this was happening, and so maybe that wasn't the most secret conversation, who knows? But it's obviously, people used to meet in person to talk about secret stuff, and now they have to fall back to video, and so the targets are, I feel like they're pretty juicy here. Like you could do a lot of damage by knowing what happens in people's video conversations. Okay, so you might be asking, what about on-prem solutions? And then this is like, I think this comes up a fair amount. So you can imagine like, I don't know, let's say you're Walmart, and like you really dislike Amazon because like they're your competitor, so you like don't want to run on Amazon's cloud. You say like, no, it's no problem. Like we'll take some software and just run it on our premises. Like we have our own private cloud, or we have like our data room, and so like if we did that, we wouldn't have to trust like as many people. This is called the on-prem solution. So what's wrong with the on-prem solution? There's some important drawbacks. Okay, so the first thing is that like latency matters a lot in video, and so unless you want to sign up to like basically run Cloudflare, it's you're taking on a big responsibility to try to like run your own like on-prem machines. So that could be a problem. The other thing is that, like, I've actually heard this from big companies who, when we were like still in Keybase days, they were considering like how to, like, imagine you run like one of the biggest companies in the world, and like you want people just to be able to message back and forth, right? And so you could use Slack for that, but then it's like the same as like the last slide. Like you have to trust Slack to get everything right. And then, well, fine, maybe like there was this thing called HipChat like 4 or 5 years ago. So you just like run HipChat on like servers in your premises, and like you just get like new code downloads from HipChat, and you just like, you don't have to worry about like the HipChat engineers like breaking into your machines. But there's this problem where like you still need people in your company to like to have access to these machines, because these machines like have hard drives and network cards that get fried, and like you probably don't want the people who actually physically access the machines to have access to this company data. Like it could be very sensitive, and so if the COO is talking to the CEO or something, like you don't want the network administrator to have access to that. So that's another kind of a drawback to this on-prem model. And the last thing is like, it's kind of interesting that, if this thing happens to have a bug in it, and like, there are lots of bugs these days that are pretty bad, like SolarWinds or Log4j, like all of a sudden, like this thing, like the software that somebody else gave you to run your premises can now become like a whole past your perimeter that like the bad guys can get into. And this happens like a lot. I mean, not to point fingers, but this is like a Microsoft Exchange thing that happens a lot, where like a lot of people run these Exchange servers on-prem, and they have some pretty bad bugs, and that's like a way that like the bad guys get in, to these like local area networks. So, I mean, the on-prem system, it doesn't seem like it's the perfect answer. Okay, so what does work? So my involvement at Zoom has been mainly involved with end-to-end encryption, and so the idea here was to take Zoom's video software and try to get end-to-end encryption, where the endpoints can encrypt and decrypt, and the server just can't possibly understand what's happening because it's just encrypted information that it can't decrypt. So the roadmap that kind of we followed was in May 2020, when we first got to Zoom, we wrote this white paper that you had the privilege of reading, and hopefully it wasn't too onerous. And it was kind of this roadmap. This is what Zoom's going to do. And at that point, like Zoom had a little bit of a security deficit. I don't know if everyone remembers, but they got in trouble. Like there was a pretty bad. There was some like negative publicity about problems with Zoom security, and I think they decided it made sense to make a big investment in their security. And so as part of it, we had a very public kind of announcement as this is how we're going to improve encryption for Zoom meetings. And a couple, 3 or 4 months later, this was the first end-to-end encrypted Zoom meeting, so it was possible to make a lot of progress in a small amount of time, and then a lot of this had to do with just the way the system was set up before we got there. So, how does encryption? How does the Zoom system work? So let me spend a couple of minutes with that. So the way Zoom works before we got there, and the way non-end-to-end encrypted meetings work in Zoom now is kind of in the form that the server. So here's Alice, Bob, and Carol. They all have Zoom. They're all talking to the server. The server generates a 32-byte random key, right? And this is called MK, this meeting key. And then it uses TCP connections to send this meeting key out to Alice, Bob, and Carol. And then once everyone agrees on what that key is, then the transfer in Zoom is over UDP. And so you can't really use, as far as I know, if you want to use UDP, you're kind of probably doing some lower level encryption on your own. You're probably not going to use TLS, because a lot of times I think TLS is meant to work with TCP. And so basically each packet is encrypted using this meeting key or key derived from this meeting key. And so everyone can encrypt amongst Alice, Bob, and Carol. Everyone can decrypt. The server can encrypt and decrypt too. And that's actually kind of important for a lot of features that Zoom provides. So one of them is like this PSTN. So PSTN, oh my gosh, what does it stand for? I've heard of POTS, which is plain old telephone system. What is? Yes, exactly. Plain switch telephone network. Thank you, Nikolai. Yeah. So, if you want to call into a Zoom meeting on a regular phone call, on a regular phone line, obviously your mobile phone or a lot of like the old school phones that you used to have in people's houses, like they don't understand the Zoom protocol, so they're just talking regular phone protocol. And then it's up to the server to, to decrypt the information that Bob is sending and send it in plain text over the phone system, and vice versa to take, if someone's calling on the phone, to take that information, encrypt it, and send it back out to Alice, Bob, and Carol. And so what that gets you is if the network link is compromised between Alice and the server, you get protection there as you would in the case of TLS. Obviously if the phone line is compromised between the phone and Zoom server, like there's nothing we could do about that. Like that's basically, a problem. And but this at least allows like something that looked a lot like I showed you on the first slide. We're just these kind of connections between the users and the server are at least encrypted point to point. And so like the phone is like one example of like this like where Zoom actually needs to know the clear text, and like another thing like cloud meeting recorder is actually quite popular. And so Zoom, I mean I know everyone uses Zoom like for class or like maybe for talking to their friends, but like Zoom has like a really kind of important enterprise sector in its business, and so it serves a lot of financial services companies, and a lot of them need to have every meeting recorded just for like compliance purposes. And so, if you ever like call up your bank and like want to dispute a charge, they'll say like, oh, this is like on a recorded line or whatever. And so I think a lot of times FinServ, financial services, needs to like record every meeting that happens in an organization, and they would do that through what's called a cloud meeting recorder. And so in cloud meeting recorder, it's like the server like has to know everything because it's going to like encode it as like an MP4 and like write to disk somewhere. So that's like another thing that's pretty important that some Zoom customers need. So in end-to-end encryption, we basically used a lot of the system that currently existed in terms of, the end goal is that Alice, Bob, and Carol are going to have this meeting key and use it to basically encrypt and decrypt using AES, which is the most common, encryption cipher around nowadays. But, what we changed is how they negotiate what this key is. And instead of the server generating it, one of Alice, Bob, and Carol will generate it and then find a way to communicate it to the other people in the meeting, probably through the server, because they basically can't, it's not practical to expect them to talk directly to each other. I mean, they're probably across the internet. And so using some sort of cryptographic protocol to distribute this meeting key between the participants. So that's more or less what happened. Now, as soon as we say the server's not allowed to know this meeting key, then you now are in a scenario where like you can't use like this PSTN dial-in function or like the cloud meeting recorder, so it does kind of turn off a bunch of different features that are available in some Zoom meetings. So there's a little bit of a trade-off here. And somebody asked a really good question, could you actually get cloud meeting recorder to work in this scenario? And the answer is yes. And kind of go into that if you're curious, but it's complicated. It's not going to be this like very simple, like our goal was to try to keep more or less meetings almost exactly the same as they were before, and also the experience of the customer to be exactly the same. And so, if you had a solution where the customer has to run some new code in their infrastructure, in their, somewhere in their cloud or, in their on premises, and like, it's doable, but it's like, getting a little bit more complicated. So for the most part, if you turn on end-to-end encryption, you turn off some features of Zoom. Okay, so I'll stop there. Any questions so far? Okay, I keep going. I can talk a little bit about the key generation protocol. Okay, so and this is in the paper. So the idea here is Alice. She's like the host of the meeting. We call her the leader because it doesn't necessarily follow that the host and the leader need to be the same person, but I think for most intents and purposes that they are. So Alice is like the host of the meeting, and she uses a random, some sort of random byte generator to generate this end case of 1 on her computer, and now she says, great, I need to get it to Alice and Bob. So before we all got into this protocol, when people sign up for Zoom and end-to-end encryption is enabled for them, they generate a long-term signing key. So they have a secret side of that key, they have a public side of that key, And this is going to persist across meetings, and it's just for signing. So now what happens is when they join the meeting, they kind of post up to the server, here's my public key. And the idea is that basically the server is going to more or less broadcast these public keys back out to everyone else. So Carol posts hers to the server, and the server broadcasts it back out to Alice and Bob. For the purposes of this meeting, they're going to generate these ephemeral encryption keys. So Alice is going to have a public key and this a secret key, and they're going to be Diffie-Hellman keys that they're just going to use for the purposes of this meeting, and then they're going to throw them away. The next thing they'll do is they'll sign their ephemeral public encryption keys with their long-lasting signing keys and kind of send this message back up to the server. So now for every user, the server knows the public key for signing, and they know a signature over their public key for encryption. And now, Alice goes and receives this broadcast, and she's able to perform pairwise Diffie-Hellmans with everyone else in the group. So, first she'll probably want to find some way to check the signature on this ephemeral key is correct. And so she'll want to make sure that Bob's signature is correct over, over his encryption key, and same for Alice, and same for Carol. Now, we need to get into a big discussion as to how does Alice know if she has the correct public signing key for these users to begin with, and that's basically the whole second half of this presentation. But just say for now, Alice had some way to know Bob and Carol's long-term signing key, and then she can verify the fact that the encryption public keys they're using for the purposes of this meeting was the one that they generated. So Diffie-Hellman is a way for Alice and Bob to come up with a shared key together. And so the way it works is Alice takes her secret key and combines it with Bob's public key, and that produces a shared secret. Meaning, if Bob were to do the opposite, if he were to take his secret key and Alice's public key, they'd both wind up with the same secret. And it has this nice property where, if you know the public keys, if the bad guy knows the public keys of both Alice and Bob, the bad guy wouldn't be able to derive that secret. So this is basically, Diffie-Hellman allows Alice and Bob to share a secret together. And what's going to happen is that shared secret is going to be used to encrypt this meeting key, and then send that meeting key to both Bob and Carol through the server in a way where the server can't decrypt the message. So basically use Diffie-Hellman to come up with a shared key, use that shared key to encrypt the meeting key that everyone needs to agree upon. Now everyone gets the same meeting key and can more or less proceed the way they did before in the enhanced encryption case. So enhanced encryption is just regular encryption, basically. So now what happens, let's say Carol leaves, and this happens because people, enter and leave Zoom meetings all the time. So basically Alice needs to just redo this protocol again, but with a new meeting key. And so she'll just generate a new meeting key. And this way, if Carol leaves the meeting, but she still is in collusion with the server, where the server is, oh, Carol, you're out of the meeting, but I'm still going to send you the ciphertext. Carol still can't decrypt because she has the old meeting key and everyone moved over to the new meeting key. So key rotation is just a way to make sure that as the membership of the team changes, that only the people in the meeting still have access to the current key. The same thing is useful before someone joins. And so let's say Alice and Bob are saying a lot of bad things about Carol. And Carol joins the meeting, and they shouldn't be able to. Carol shouldn't be able to hear what Alice and Bob were saying before she got there, right? So, for the same reason that it rotates after she leaves, it also rotates, before she joins. And so basically, ideally you'd rotate the key anytime anyone entered or enter or leaves a meeting. That's the ideal scenario. But you could think about these, cases which are actually quite common. Let's say you have a meeting that starts at 3 o'clock and everyone joins in the first 10 seconds, say 500 people joining in the first 10 seconds. Because by the way, the system does scale up to 1,000 users. So you can imagine a lot of churn happening where you're just like constantly regenerating keys in such a way where it would just cause a lot of extra network traffic just to be rebroadcasting this protocol for everyone who joins. The same thing with leaving. Like if everyone leaves at the same second, because usually they do when the meeting's over, it makes sense not to just like spam the system with like tons and tons of key rotations. And so like the paper says like basically these are bashed into 15-second intervals just to prevent a ton of churn. And so another question that actually got asked, which is a good one, is like, is there like a performance impact of this? And the answer is largely no. There's basically no performance impact that you could really measure in terms of like cryptographic operations. And so the good thing about Diffie-Hellman nowadays is, it used to be slow, 30, 40 years ago, but nowadays you could do like 10,000 of them per second on your on your computer, on your laptop, probably a lot more. So it's gotten very optimized, and obviously the hardware's gotten a lot faster. So you could do like a lot of Diffie-Hellmans, and like that's not really the bottleneck. But there is like a network bottleneck, and the thing about Zoom is they've taken great pains to make their protocol as network efficient as possible. And it doesn't really matter if you're sitting in your dorm room on a gigabit connection, but it matters a lot if like you're on a 3G connection on your phone, right? And like high latencies and stuff like that. And this is like I think a lot of the reason why some video protocols might be better than others. Like how are they doing in really bad network conditions? And so you can imagine a case where like someone's like coming into a meeting and they have like a really bad connection, but it's enough. Like you actually don't need much bandwidth to have like a phone conversation. Like to do audio only in Zoom, it's like a very small amount of bandwidth. But like if you join the meeting and you get like slammed with 32K worth of like crypto protocol like exchanges, that's going to really affect your experience. You like won't be able to see the meeting for like 10 or 20 seconds, and that's like not a great user experience. So in terms of like there was a question about why. I think that's what we really cared about. That whatever we were doing, it had to be like very mindful of network and not wasting network space as much as possible. Each of these encryptions is on the order of like 32 or like 64 bytes, and that's fine if you have to do one of them. If you have to do 1,000 of them, now you're talking about real cost that you want to really engineer around. Okay. I'm about to move on, but yes, question. Yes, that is. Yeah, the network topology here is really a star topology. Everyone's like more or less connecting to one server, and so I think if you did that, let's see, yeah, because you're saying like the bottleneck would be Alice trying to like her uplink would be the real. If you have to send out 1,000 ciphertexts and Alice trying to send 1,000 of them through her connection would be that would be the bottleneck. And so you're saying like maybe instead of Alice doing that, she could just do 20 of them. She only has to upload 20. Then Bob will do the next, and he'd only have to he would take some of the load and he'd do another 20, and you keep passing it along. That would work. I'd be a little bit worried about like lag there because like you're talking now round trips for like for this key to propagate. It depends like what your deadline was, right? And if it's time sensitive and it's like for people to get into the meeting, that might be like an unacceptable delay because sometimes you could have like 100 millisecond ping to the server, in which case if you have to do this like 10 times, then all of a sudden that's a second or like 2 seconds of meeting that you'd be missing. But yeah, I think Bob definitely can, and I think we have a certain protocol for webinars where we do consider something like this because like webinars need to scale to like 10,000 or 50,000 people. And so in that case, yeah, I think we did actually propose something exactly like that. Yeah, but it's a good point because Bob and Alice basically know the same. And, yeah. Yeah. Because okay, then MK1 and MK2 are randomly generated 32-byte keys. So MK1 is different from MK2 just because they're both different poles from the same random number generator. The Diffie-Hellman shared key between Alice and Bob is always the same, but it's just using to retransmit the different MKs, right? And so, okay, great. Good question. Yeah, Nick. Okay. That's a great question. Well, there is this cryptographic heartbeat protocol, but that's not how. I think basically there's a lot of metadata going back and forth between the clients and the server. So the server, even though it doesn't have the ability to decrypt, it has a very good notion as to who's in the meeting, what their IP address is, and potentially some sort of metrics as to network connections. And so the server has a very good idea who's in the meeting and who isn't. And there's a heartbeat protocol that is there for all Zoom meetings between the server and the client. So the server always has its notion of the roster, and that's usually very up to date. And so it's the same in an end-to-end encrypted meeting or a regular meeting. I think a lot of the engineering here was to use as much as possible from the existing meetings and just to add a layer of key exchange on top of it to more or less transfer over to an end-to-end encrypted system with using as much as the old infrastructure as possible. Yeah. The server does inform all the clients. Yeah. Yes. So this is a good question. So the question is, let's say Carol's leaving the meeting, and Alice needs to rotate after Carol leaves. And so Carol just, is shown as she's still in the meeting, but she is, and the server's making it seem like Carol didn't leave. And so then Alice doesn't know to rotate the key. If your video is off, it would be a hard thing to fake. I mean, the server would have to rotate through old video, or it would have to do something like that. But it certainly could do that. Now let me see if you could solve that problem if the heartbeat protocol was more interactive, right? So I was just about to say every 10 seconds the leader will send a broadcast as to who the leader thinks is still in the meeting, right? And so that's actually the next slide. And the heartbeat protocol is of the form that the leader is basically broadcasting to everyone else in the meeting, here's who I'm encrypting for, and this is the latest generation of what the key is. And so this way, all of the users are synced as to what the leader's view of the world is. And if you're Bob and you don't hear from Alice for 4 or 5 heartbeats, right now the system just throws you out of the meeting. It just, if the leader wasn't transitioned to someone else. So there is a way if the leader is, if the server coordinates the fact that the leader is going to leave the meeting and the new one's going to take their place, then there's a cryptographic protocol to make sure that everyone knows that the leadership has transitioned. But in the case where the server did not inform the other users of that and the heartbeat just disappears, then the protocol is right now that everyone just hangs up if they don't get a recent heartbeat. Now, that doesn't solve the problem you were talking about, though, because let's say an evil server, just Carol left the meeting, and she finds a way to just loop. Yeah, let's say it just finds a way to replay her. No, there's replay protection in the protocol, so I think it can only do that without video. So then the leader would see well, Carol's video went out, but yeah, it could do that and suppress the message that Alice left, that Carol left. And so you can kind of engineer around that by saying well, now everybody should be sending our heartbeats to everyone else, and then you could avoid that attack. That's a good question. All right. So one thing to notice is that we inherited this feature from Zoom, and that is, display names, as we all know in Zoom, are pretty arbitrary, right? So So you could change your name to whatever, emojis you want it to be. And so there's no real strong notion of identity here. It's just like the identity is whatever the users broadcast to each other. And so we're going to talk a little bit later about improving that notion of what identity is. So that's important to note. Okay, so let's talk about how a man-in-the-middle attack would work, or I think the paper says, sorry, meddler-in-the-middle attack. Because this is kind of the real, it's one of the real issues with the system. And I kind of danced around it earlier, but it's something to consider. So if I didn't mention it earlier, I meant to, the server is coordinating everything about these users, right? And there's no good way in which they could talk directly to each other. So, what can the server do here? Well, it can partition Alice and Carol and give them two different views of that broadcast channel, right? So the server can present to Alice, okay, here's Bob's key, and here's your key, and here's this other key that, that's supposed to be Carol's, but I'm going to substitute my own key in there. So that's what the server shows to Alice. The server shows to Carol a different version of that. It says, here, Carol, here's your key, and here's Bob's key, but instead of Alice's key, you don't know this, but I'm going to put my key in. And so now what happens is when Alice does that same Diffie-Hellman, she's going to perform a Diffie-Hellman between her and the bad version of Carol. And so once she does that, she's going to then encrypt the meeting key for that bad version and send it to the server. The server's then going to pick that up because it picks everything up and can decrypt it. So now the server knows the meeting key. But, Carol will be none the wiser because, the server will just do the same thing for Carol. It'll take, the server's pretending to be Alice as far as Carol is concerned, so Carol will get this key. She'll think she was talking to Alice, and then the meeting will run as it did before, but by the way, the server knows the key. And so this is the classic man-in-the-middle attack, and it's basically, it's more or less an issue with any public key-based protocol you can think of. Certainly your browser, when it does TLS, Signal, everyone's got this problem, right? So how do you solve it? Well, in phase one, the answer is this slightly annoying protocol, which, we don't think many people actually do. And so, everyone should do it, but, it's a hard thing to do. And so basically what needs to happen is there needs to be some performance where the leader is going to announce out to the rest of the meeting, basically here's my public key. They're going to say it in the form of 8722528882, and everyone's got to listen to that and make sure their computer says the same thing. And if everyone's, of the form, I heard the key being read out, I know it's the same key that I have in my window, I'm not going to say anything. And if it's the wrong thing, somebody's no, stop the meeting. And so this has to happen more or less every time the leader changes. And in your client, if you have end-to-end encryption running, whenever the leader changes, you would have to do this. It would tell you, oh, the host now changed. The encryption key is updated. Please verify again. So if you did this protocol, question, how does that prevent the attack that I showed before? Let's say everyone does it. Yes? The window would show whatever it thinks is more or less the public key of the host. So if you're the host, it'll just show you your own public key back. And if you're Carol, it'll show you the hash, basically, of what it thinks Alice's public key is. So you're saying, I'm sorry, are you answering the question I asked, or are you asking a different question? You're asking why? What?
I'm asking the first question.
Okay. You're answering the first question.
No, I'm asking.
Oh.
I'm not convinced it's going to work.
Oh, you're not convinced it's going to work. Yeah. Well, Zoom can't control the way the software works on your computer, right? The software's out, the client has instructions that it knows Alice is the host, and it thinks it knows Alice's public key, and so it's basically presenting. So let's say I'm Alice and you're Carol. So it's presenting what it thinks Alice's public key on your client, right? And if it got the wrong one, so let's say the man-in-the-middle attack happened, right? And instead of showing you Alice's public key, it showed you the evil public key. You thought Alice's public key was not the real one, but it was the evil one. So your client would actually show that to you because it's not going to do both. It's not going to show you the fingerprint of a public key that didn't think corresponded to the leader. So in other words, you've done this protocol. You did a Diffie-Hellman with Alice, right? And Alice signed her Diffie-Hellman with a long-term public key, right? And it's basically going to show you when I did that protocol, this is the public key I used, and it'll show that in your screen, and I'm going to just read out that same thing. So if it actually was the same public key, you get the same answer. If it was a different one in this man-in-the-middle attack, I would read something, and it just wouldn't correspond to what I was reading, because there's no way that the server can generate a collision in this hash where it would be able to come up with a different public key that had the same fingerprint. So, sorry, yeah. Yes, that's definitely possible. Yeah. Yeah, I mean that's like the deep fake attack, I would call it. Yeah, and it's definitely possible. It's like we're raising the bar a bunch here, but yeah, it's definitely possible. Okay, I don't know if I totally answered your question yet, but okay. Yes, absolutely. Yes. So the whole thing assumed that the software is correct. Yeah. So So what attacks can we think of? So we mentioned deepfakes for sure. A bad binary. So one that only ever shows the attacker's fingerprint, even though it used a different fingerprint. Only ever shows Alice's fingerprint, even though it used an attacker's fingerprint, would totally break the system for sure. So we're assuming that the code we ship to you is the right code. That's a very debatable question. I mean, we can get into a lot of philosophy around that, but if we don't assume that, we can't do anything. It's we're dead in the water. So we need to assume we have some way to give you code that does what we say it's going to do. And we could go into, if people want, in depth about that. So there are other attacks. So the deepfakes was changing the audio. So this is one that actually we thought a lot about. So when you join an end-to-end encrypted meeting, it's the same way you would join a regular meeting. You just click on that link and you're there, right? Now, the server is the one who generated that link, and it could show you, it could just someone working at Zoom could click that link and then join the meeting, right? And so in code, it was extremely important to us to know that there was a one-to-one correspondence between the people we had encrypted for in that key exchange and the squares on the screen, right? And so if you're in a meeting with only 3 other people, if you've only keyed for 3 other people, we were 100% certain we'd only show you 3 squares. And there was not going to be a case where we actually encrypted for a 4th person, but they didn't show up in the gallery view. So in that way, the guarantees are very closely tied to the UI. And so the idea that anyone at Zoom can join the meeting, but if they joined, the leader would be able to see them. That's the important guarantee we can get, and that's about the best we can do given the UI considerations that clicking on this link allows you to get into the meeting. So I mean, it's something I thought a lot about when we implemented this. Another one that was kind of tricky that we thought of was imagine you join and drop the meeting for a split second, once every 15 seconds. If you did that, you would never show up in the gallery because you basically weren't there long enough, but you'd get every iteration of the meeting key, right? And that would allow you to decrypt the whole thing. So what happens in that case is the participant list that I showed here, oh, sorry, I went back too far. Where's that list? Yeah, the participant list here, if you join and drop a bunch of times, it's going to show you that. It's going to say like, so-and-so like join and drop the meeting like 50 times. And like that's the reason why, because otherwise there'd be no way to detect that attack. Let's see, what else? Any other ones I can think of? Oh, we could talk about accessing end-to-end encrypted meetings via the web, because there was a question about that. Okay. So, a lot of different, this is a debate we have a lot internally. So you need to access an end-to-end encrypted meeting through a Zoom client that's either distributed through the App Store or like you download it to your computer, right? And Zoom has this ability to access meetings through the web, right? And so why is it not possible, to do the same thing for this end-to-end encrypted protocol? Well, the answer is it is totally possible. You could very much do this. You could take whatever protocol I just described, put it in your web browser, and that should run without a problem. But now, there's this issue with distributing code via the web, which makes it, what some people argue makes it less secure, and especially in these end-to-end contexts. So, let's say you had a binary that you're running on your computer, and you suspect it of being like, well, first of all, there's a pretty good guarantee that everyone's going to get the same binary. And this isn't hard and fast, but a lot of times it works out that way. Like the iTunes store is the one that will send you the iOS binary. The Android store, the same thing. If you want to download this binary from the Zoom web, like there might be some chance to send one person one binary, the other person another binary. But in general, it's a lot easier to get this property where everyone's dealing with the same, software artifact. And so if anything's wrong with this, if there's like a backdoor put in it, you have this like kind of, not a guarantee, but a little bit more of an assurance that you have to widely disseminate this backdoor to a lot of different people. And if you were to do that, somebody might find it. And that would dissuade, an evil version of Zoom from actually, doing this. That's not really true from a web page perspective. And so if you think about every web page you go to, you load it up, and it can send you whatever code it wants, and it could definitely target you and send you like a version of JavaScript that didn't send anyone else. And there's very little in the way of artifacts left after you close the tab, right? And so you can kind of concoct a scenario where if like somebody wanted to get into your Zoom end-to-end encrypted meeting, and you allowed people joining in from the web, they would just, Zoom would just backdoor this version of the app they're using on the web, and it would be, very hard to detect, like a lot harder than if they were just, sending you a bad binary. So, this is always a question we have internally, should we allow this feature? But we think it's a little bit dangerous because of this attack. So, this might be a way to break into a meeting. One day you go to Zoom, and like it says, good news, now you can join end-to-end encrypted meetings from the web, click here. And it's just like, it's an evil version of the software. So that's like another attack that's theoretically possible. Okay, one more thing I wanted to mention. There is this feature which is quite useful if you're concerned about man-in-the-middle attacks, which is locking the meeting. And so imagine you went through this whole protocol to like, I'm going to read the server codes, and you're going to listen to it, and we're all going to say yes or no. You could push this lock the meeting button, and once you do that, then no one else can join the meeting. And so like, even if somebody drops out or the leader changes, you wouldn't have to reperform the protocol because that the roster of who's cryptographically allowed in the meeting can only shrink from that point on. So this is a pretty good cryptographic guarantee if you add that with meeting codes to do a better job of kind of making sure that someone's not going to get into your meeting. All right. So it's a good time to stop and take a quick break and ask anybody any questions on all this stuff to begin with. I'm trying to like hit some of the questions I remember seeing that were asked. As I could think of them, and I'm sure I missed a lot of them. I'll get a little bit of water too. All right. So that wasn't good. I'll go get that. Okay, so I think somebody asked like, what's deployed and what isn't deployed. So everything I described so far is deployed. And unfortunately, it's a little bit hard to find. But if you have your own version of Zoom, or if you work at a different company that has this feature enabled for their account, you can use end-to-end encrypted meetings. I use it all the time. It's basically almost impossible to tell the difference. It's very similar to the existing Zoom meetings, aside from those features you can access. There was a question about chats. So, in a Zoom meeting, there's like that thing where you could chat inside the meeting. And so that's pretty easy to do, just with what I described. You could more or less use that same meeting key to encrypt the chats back and forth. That's not a perfect security property. It's basically that only people in the channel can encrypt or decrypt those chat messages. But you lose this nice feature that a lot of chat programs have of like digitally assigning authorship. And so we're not, in the chats, people aren't signing the messages. They're just encrypting them. And so there is an attack if the server is actually colluding where, Alice writes something into the chat, but it actually says Bob said that. So that would be possible in the chat implementation. But it would not be possible for the server to read what's being chatted. Yes? That's a great question. I was just going to answer that. If you do private messaging, then you use Diffie-Hellman key exchange between the two different participants. So in that case, you have a much better guarantee against that third person getting into your chat. Yep. Yes? So the question was the reaction icons? Yeah, that's also so basically everything is encrypted using the same symmetric key. So the reactions too are encrypted. And we have a kind of the philosophy where in an end-to-end encrypted meeting, either it's encrypted or it's not available. Like we do not want this kind of weird case where like this feature's here and it may or may not be encrypted, because that's like very hard for users to know what's going on. So when we first launched this, we actually had disabled a lot of those features like reactions or chat, let's say, and we just added them back in only once they were encrypted. So Whiteboard, it actually works too. Screen share, like everything basically works on the same key in the same encryption scheme, which is, each of those required a little bit of extra work, but if they're in end-to-end encrypted meetings, then they're encrypted. And if they're not encrypted, then they're not enabled, is the philosophy we had. Okay. Great. Well, I guess, it might be worth talking a little bit about how we can make better identity. So this is what we're currently working on. And it's a little bit more complicated, so it's taking a little bit longer to get out the door. And, we're probably not going to get to all of it, but it's worth discussing the general ideas here. And so really what we want to get to is a point where if you and I are talking every day, I should remember your public key. I shouldn't have to redo that leader key exchange every time, the code exchange every time I talk to you, because that's just a silly waste of time. And so the very basic idea here is that, if I write down your public key on my client, then the first time I talk to you, I am susceptible to some sort of attack, but every time after that, I'm not. And so the window in which the server can mount one of these man-in-the-middle attacks is very much reduced. It would have to be the first time. And does anyone use SSH? Like this happens in SSH, right? Yeah. So the first time you connect, like, do you want to trust this key? Yes. And every time after, it'll say it won't. And if the key changes, it'll say, the key changed. So like it's the same idea, but for Zoom meetings. But we quickly get to this point where like, Alice and Bob have like 3 different devices each. So what does that look like, right? And the problem is you basically can get warning overload here. You can get quadratic warnings. If like Alice has 3 devices and Bob has 3 devices, they have to say like, yes, I remember Bob like 9 times. And it won't be totally obvious to them why they have to do it, right? They'll just be like, I thought I pushed this button, but I'll push it again. So that's an issue. And then of course, if Bob adds a new device, it's like the same, same thing all over again. So our thought was that if this warning would become very ineffective if it happened every time the user changed their device. So we kind of went down this path where how can we get to the idea of like these personal device clouds? So like Alice has a cloud and Bob has a cloud, and as long as Bob has introduced this new device into the cloud, that's fine. Alice doesn't really need to know about it. And so, then you get this kind of idea like, oh, you've never met Bob before, and so you might see that the first time, but when Bob then adds a new device, you won't hear about it. And so this is kind of the motivating idea behind this, phase 2 and beyond in the white paper. Another thing that's kind of cool about this is like once Alice and Bob have these personal device clouds, now they can gossip information across their devices in a way that's encrypted. And this is actually quite useful. If we're going to be in a position where we're now accumulating, basically these durable records of who everyone's talking to, it would be a little bit bad to like accumulate that in like a big database in clear text on the server, because if that ever gets hacked, that's like a pretty bad thing to be out in the wild. And so now the idea is that when Alice and Bob are making these lists of the people they've spoken to over the last year and whose cryptographic identities they're remembering, and they need to gossip that across their devices, they can at least encrypt that. So if like a bad guy stole it, they wouldn't know exactly who Alice and Bob were talking to. And I think SSH does something a little bit like this now. Like they used to basically, they used to put the public, like the IP addresses in plain text, but now they just store the hashes of the IP addresses. And so it's a little bit, it's not exactly the same system, but they've certainly thought about, similar ideas. Okay, so how do we implement these personal device clouds? Well, I think we have this notion where Alice is going to have three different devices. In this case, her laptop, her phone, and her tablet. And when she adds a new device, it's going to have to be approved by an old device, right? And this way, the server can't just add a new device for Alice and say, oh, well, I'm going to pretend to be Alice and just going to log in as her. That shouldn't work because Alice would have to approve the addition of any new devices into her device cloud. And so I already described this. When Alice, approves a new device, she's expanding the circle of trust, and now her devices are delegating authority to one another to speak on behalf of Alice, and they're also gossiping these private keys and secrets so they can sync without server trust. The other thing to obviously have a case for here is that when Alice leaves her phone in a taxi cab, it has to be revoked. And so one of her existing devices has to say, Alice's tablet in this case says she no longer is using that phone, and that way if a bad guy picks up that phone, it won't be able to be injected into a meeting acting on behalf of Alice. And so that's another important feature of these device clouds. So how is this actually implemented? And this is where we kind of get to this idea of a chain of signatures. And so when Alice first provisions her first phone, link number 1 in this case in this chain is that she has a phone. Her phone is signed by itself. But and then she'll go to her laptop, and when she does that, another signature is generated saying, I'm Alice, I'm signing in on this laptop. And we kind of came to this idea at Zoom, which we did not have a Keybase, that we didn't want Alice to be forced to bring these two devices together at the same time. And if you can do that, it makes things a lot easier. But we figure like the corporate customers who are using Zoom might not have that ability. They might have a machine at home. They might have a machine in their office. And those two machines might never meet each other. And so it's actually a different signature when Alice goes back to her phone and approves the addition of her laptop. And so that's like a third signature in this chain. And maybe a fourth signature in this chain is, well, I'm now going to use my laptop to revoke my phone. And the way these chains work, that Alice is always signing the thing she's doing, and she's signing the state of the world that predated her, so she'll sign a hash that basically represents the rest of the chain that was there when she actually did this operation. This allows her to kind of accumulate these what we call personal device clouds. And there are a lot of attacks against the system. So once you sit down, well, this makes sense. Alice is accumulating this kind of append-only cryptographic data structure. What can go wrong? Well, so there are a bunch of things that can happen. This first one is I'm calling a withholding attack. So if the server is the one who's in charge of maintaining this record of Alice's signatures, and Bob comes along, I mean, it could show to Alice, oh, hey, I know you revoked your phone with your laptop, but when Bob shows up, it can just chop off the end of the chain and say, like, well, here's Alice's chain, and yeah, the phone is still valid because I'm going to leave off the revocation. And that's actually could be quite a devastating attack if Alice is trying to revoke things and the server is withholding that fact from other people. So that's one such attack that you can imagine. The other thing the server can do is can try to fork Alice's view of her own view of what her chain of signatures is. And so if she's made these 4 signatures and she tries to go and make a 5th signature, the server can kind of leave off the last one and say, well, you've only made 3 signatures and just build on top of that. And now the server has coerced Alice to fork herself. And so in this case, again, the server can drop off can chop off this last thing that Alice signed. And again, hide the fact that Alice revoked one of her phones. And another thing the server can do too is it can just wholesale send a different chain to Bob. And so Alice was very careful. She signed everything as it was, but how is Bob going to know if the server just sends her something totally different? And so this is another attack as well. I mean, you'd like the fact that Alice and Bob, when they ask for Alice's signatures, to always get the same answer. So in Zoom, what we're building is something a lot like what we did at Keybase, which is something called a transparency tree or Merkle tree. And we've kind of, I'm probably not going to have too much time to go into all the details, but the general idea here is that we want some way to represent the state of everyone using the system very succinctly, so that as long as you know, let's say, a 32-byte piece of data about the state of the system, you can then recover everything else there is to know about it. And so in this case, if Bob and Alice can agree on this 32-byte signature, they can then come to an agreement upon Alice's devices and Bob's devices in such a way where any of these different attacks that I described can be detected. And this is, this type of idea is showing up in a lot of different systems. It's already in Keybase. If you use certificate transparency in your browser, it's using something quite similar to this. Key transparency is a similar protocol for GPG keys. And there's this paper out of Microsoft called Seamless that's doing the same thing. And it seems to be a pretty popular idea. And the overall setup here is that the server is maintaining this pretty complicated data structure. The clients are accessing it from time to time, but they want to do it in such a way where they're guaranteed that there's some consistency in the data structure without potentially having to download the whole thing. And so the solution here is a transparency tree. And in particular, as long as Alice and Bob can grab the same root, they can then chase a whole sequence of signed statements up to the fact to know that the same root implies the same chain about what Alice's identity was, what her different devices are. And it would prevent most of the attacks I spoke about in those earlier slides. So because I think it's so interesting, I was just going to jump into a little bit about how these are actually implemented. Unless let me stop for a second and ask, are there any questions? Okay, no questions. All right, so how are these? I mean, these trees show up all the time. They're very interesting. So just spend a couple minutes thinking about how they might work. All right. So imagine there are 2 users, and each of them have 2 signatures. There's Alice and there's Bob, and they each have 2 links. So I'm going to pick for this example a very bad hash function that you should not pick. My hash function only outputs 1 byte worth of data. Okay, why is that a bad idea to have a hash function that outputs only 1 byte worth of data? Yes? Sorry? Yeah, exactly. It'd be very easy to generate collisions in this hash function. Yeah, you just trail the outputs, and the one thing a hash function has to do is is make it hard to get collisions. A collision is where you input 2 different values and get the same output. And so with a 1-byte hash function, that's not going to work. But I picked a bad one. Okay, so Alice wants to store link sub 1 is like some statement of the form I added a phone, and link sub 2 is a statement of the form I revoked that phone. And so what we're going to do is basically we're going to let me see. Right. So basically what we want to do is store this value in the tree, which is a hash of, I'm Alice, this is the first thing I'm saying, and this is the thing I said. So in that case, that's h of Alice concatenated with 1, and this other thing links of 1, and that gives me the value 12. And Bob does the same thing, and we get the value 34, and for a second link, and he does basically 4 different input values, 4 different hashes, and these are the 4 things we're going to store in this tree. Now, the question is, where do we store them, right? And that's, and this is the question, this is like the path that you want to follow through the tree in order to get to that value. So, for Alice's first link, we're going to take the fact that it's her name, Alice, and it's her first link, and hash that, and that's going to give us some value, again, a 1-byte value, and that's going to tell us where in the tree that it's going to be stored. And so in this case, it's like the value is 001, which means it's going to be in this link all the way to the left of the tree. And when her second link is going to be stored under the path, the hash of Alice and the value 2, and that gave her 0xc4. And so basically, the 2 different parts of her identity are split on different sides of the tree. So how are we going to boil this all down to 1 hash value? Well, now the answer is we're just going to recursively hash everything, right? And so, we're going to take the 2 leaves on the left and the 2 leaves on the right, and those are each going to give us an internal hash value, right? So in this case, we're going to hash the path, the value stored there, and then for the other child, the path and the value stored there, and this will give us a different hash value, right? And so now we have 56 for this internal one and BC for this last one, and then one more time we do this. And then now, the same thing. We're going to hash the prefix of the path. And so in this case, Alice is all the way down here. There's some long values starting with 0, 0. So we're going to go 0 means left, 0 means left, and wind up at this leaf. Alice's second link over here starts with 1, 1. 1 means right, and 1 means right, and we wind up at this leaf. And so basically, this is a tree where we're hashing the paths, and eventually the value stored at that path, and it's going to boil down to 1 hash value. So that's more or less the way it's stored. Now the question is, how do we look something up? Well, the first thing, so in this case, we're going to look up the leaf for Bob. And let's say Bob has, we're trying to get the second link he hashed into this tree. So the first thing we're going to do is we're going to query we could figure out the value of this path by taking the hash of Bob concatenated with 2. And so that'll give us, I guess this one right here, that value is 42. So we get 42. We're going to query the server for this Bob, 2, like we want Bob's second link. And then it's going to give us back a bunch of different data. It's going to give us back this value here, the value 12, because that's the neighbor of it. It's going to give us back the value of the link that's actually stored. So that's the thing we actually care about. And it's going to give us back this other neighbor here, because we need to hash, we need to hash this other blue node together with this node, which we can now reconstruct to get this root value. So the point is, the server's going to give us back basically log and entries, and when we hash them all together, we should be able to get to the fact that the root value has determined exactly, uniquely, where Bob is in this tree and what the actual data was. And if Bob or Alice was able to get the root value out of the tree, like through some out-of-band method, let's say it was like posted, on Zoom's website or something. Now, as long as that root value is there, it determines everything else in the tree, and in a way where the server can't lie about it, it determines that Alice's second link has to be stored in the tree in this location. Yes. Verify the what? Yeah, exactly. Yeah, because they're going to continually add more things into this tree. Like so, for every, for basically every link they add, they're going to add it to a link into basically a random part of the tree. And the idea, and yes, you need to know where to find that, which is why it's important to hash the value of the path along with the values themselves. Yes. The tree is all stored on Zoom's server. So basically, Zoom's going to have this giant database of not just today's hash tree or this minute's hash tree, but every hash tree that's ever been stored before. So it's going to store the sequence of values. And so you show up and you say, I haven't used Zoom in a long time. I need to look up Bob. It'll say, more or less, sorry, let's just do Alice. So I'm just signing into Zoom for the first time in 5 years. I want to talk to Alice. The first thing I need to do is figure out how many devices she has in her device cloud. And so I need to figure out everything in her chain. So I'm going to query the server for Alice, and the server is going to give back all those hash functions in such a way where my client's going to download them and then reconstruct the fact that they all hash back to this one hash that the root that you had when you came to the system. The cool thing about hash trees is that this stuff can be stored in non-trusted storage. You can imagine there's like a third-party mirror that has all this data, and as long as you know the root hash, everything else is determined from it. And so you can go to like a SourceForge mirror basically for this data and download it from somewhere else. But basically, it's all written to the same place. It's all written to Zoom servers. Yeah. Usually, you just use SHA-256. So yeah, that's normally the way you do it. There's a little bit. If I have time, I might change that answer. But if you're doing this for Alice, you basically need to get, and in this case, she has 2 links. You need to basically get back 3 paths. You need to get back the path for her first link, the path for her second link, and a third path that proves to you that the third link isn't there. And so that's the way this lookup protocol will go. And we can think about what it looks like to prove something isn't there. And again, it's using this fact that the paths themselves are hashed into the tree. And so, it's not going into it, but you can use the same protocol to figure out, something isn't there that you can to figure out that something is there. So I'll skip that. One thing to notice about an update here. Let's say Cleo wants to come in and she wants to store, the first part of her link, the first part of her chain. It's important to know we only need to make log and updates. And so this is the same tree there was before, but Bob got kind of bumped. Bob used to be right there. He got bumped up to right there. And then these kind of hashes in bold were the ones that had to change. So obviously, we're going to be updating this tree all the time whenever anyone adds or revokes a device. So it has to be, pretty fast to update. And of course, it's very important that once this change happens, the root value changes too. But it does because, recursively, as long as one path changes, the root has to change too. So the whole idea of this thing is that it can be audited. Yes? There's one central the answer is yes. You could definitely, you could kind of concurrently update any subtree you want. But there has to be one eventual root at the end. And so the way to handle that at scale is you can batch a bunch of them. So you could throw like 1,000 updates, into one batch, and then you basically can get infinite throughput that way. Or you can just do this kind of like distributed computation where just different subtrees get bubbled up, and then the top 2 or 3 layers could be on one machine that's just writing it. But it's important that this is a linear progression of updates, and it's not, let's say a DAG more or less. So there is like potentially a bottleneck, but we think we could get about 10,000 updates per second, which should be enough, even if there's like a one machine bottleneck. Yeah, that's a good question. Yes. I'm sorry. So the way this works is that typically speaking, the Zoom web server is going to output, here's the most recent root. Like it'll just keep outputting that. And so you start from there, and it could be the fact there's like a mirror, or it could be the fact that an auditor is always checking the fact that Zoom's outputting the right root. But given you can get the root, it always determines everything else that's in the tree. Basically, whenever you start an operation, you grab the root and you grab the path, and you should probably write it down to a database to make sure, in the case of a dispute later, you can, and these are actually signed too. And so, not only is it going to be published, it's going to be with a signature of the fact that if you find a mistake, you can say, well, Zoom signed this root, and it's in direct contradiction to what my friend over here got, and you can then present that to somebody and say something's wrong here in a way where it's entirely provable that something is wrong. But usually, so the way it would work is, and obviously if you only show up once a day, you're going to miss a lot of stuff in between. So like if you ask right now what the root is, you'll have sequence number 1,000, and you ask tomorrow to be sequence number 2,000. You shouldn't have to download all 1,000 roots in between. And so there's another thing we do is we, I think the plan, as far as I understand, as far as I remember it, is that if you work for a big company, you'll have an auditor who's always checking the state of the street all the time. And whatever you download to your client, you can double check with the auditor to make sure it agrees with what they saw. And I think, on your phone, you probably don't want to spend all the bandwidth to always be checking the street. But, your company's auditor is going to be something that's online all the time. And in that case, it can actually make sure that the root you got on your phone is the same root it got and was consistent with everything else in the progression. Yeah. Kind of skirted over that a little bit. So anyway, to kind of prove this append-only property, and so we want this property where like this is a data structure that you can't remove anything from. You can only make updates to it. And the signature chains for membership work that way, right? Remember, when you revoke, you're not deleting something. You're signing a statement saying you revoked a previous signature. So basically, if you assume, like the way these auditors might work is that if you assume any version, root, like the ith version of the root is valid, the i+1 version is, you could basically just run the update protocol and make sure that login series of node changes inside the tree have led to the next successive state. Or if it's a batch, it might be much more. But basically, you get to a point where you can audit the whole tree and log in. And if you only had some, and you've only had some kind of updates to audit, that would be like whatever the number of updates you wanted to times log in. Okay, so that was kind of a whirlwind tour. There's some really good properties about this. You can prove inclusion or exclusion of any kind of signature in login. You could update in login, and you could audit in login too, and login too. But what's wrong? So why might this be a bad idea? At Keybase, we had a very similar data structure, and we had this idea that like everyone's identity was out in the open. And so you could look me up on Keybase, and you'll see I have 8 devices. You'll see exactly when I added them. You'll see which ones are revoked. In like a corporate setting, that's not ideal. And like you do want the fact that everyone is in one kind of auditable data structure together, especially if you consider the fact that different companies will want to talk across the boundaries. But you also want to prevent the fact that like one company has to tell everything there is to know about another company, about their the device additions and deletions. That might be very sensitive information. So the question is, can we do better than kind of asking you to hash Alice and the number of links in your chain in a very transparent way? And so, the tree. I'm not going to go into this in too much more detail, but like this is where we get to some pretty interesting new cryptography, which has a lot of different usages. But instead of using a hash function like SHA-256 as I described, you could use something called a verifiable random function to allow the server to obfuscate where these leafs are being stored in the data structure. And this means that it would be hard for anyone but the server to figure out how many devices Alice had, but Alice would still be in the case where she could catch the server in lying to her if the server tried to leave out one of her devices. So it's like one of these cryptographic things where it feels like you have way too many different properties to be able to get the right answer, but it actually does work out very interestingly. And there's more about that in the paper. So I'm going to stop because we're out of time. Okay. Anyway, this is not just Keybase doing this. This is in a lot of different systems. There's a system called Comics, which I forgot to mention too, And it's all the same idea. It's like a Merkle tree with, instead of using a hash function, using a verifiable random function, which is privacy preserving, append only, auditable. And this ensures all users have a consistent view of any Zoom identity and that any impersonation attacks can be detected. So I ran through that very quickly. Skip that. And one last thing I want to mention is that I described all this in the context of meetings, but this is also useful for applications outside of meetings. So there's like a messaging app inside of Zoom that nobody uses. It's useful for that. And in fact, in these asynchronous communications, so one thing about a Zoom meeting is if it's a synchronous kind of meeting where everyone's online at the same time, you could do these things like meeting, like security code exchanges. But if you're doing IMs, it's not possible because no one's online at the same time. And so then these types of ideas for managing identity and auditable identity really do matter because there's just basically no good way we can think of to manage devices for users and get the same properties about that you get the right public keys for the users. So that's also what we're doing internally at Zoom, not just for meetings, but for other products as well. Okay, I only have 3 minutes left, so we could end early. Any questions that I left out? Sorry. Any questions anybody have? Yes. Yes. That's a great question. In Keybase, the way we did it is that given any Merkle root that you had on your device, and any one you'd get in the future, there would be a series of pointers that would always allow you to jump back to know that the one you just got from the server is consistent with the one you got in the past. So that gives you some indication that the server's not just giving random ones out to anyone it wants because it would have to keep consistency across these updates. That only answers the question partially. At Keybase, the way we did this also, the server always signed any Merkle roots that are published. And if you got one version and Alice got a different version, and they were not consistent, there'd be a lot of proof to say, there's an attack here, right? Because either the bad guy stole, our public key, or we were issuing conflicting updates to different people. So it just means that if there were a compromise, there'd be enough evidence to put it back together. But that doesn't answer your question, does it? Yeah. Yes. Well, yeah. Well, because it's a append-only data structure. So the one Alice sees is a superset. The tree is a superset of what Bob saw. And so, yeah, and they have to be linearly consistent with each other. Yeah, exactly. A good question.